Today we are going to discuss more probability rules. Recall that we discussed before the addition rule for disjoint event. If event A and event B are disjoint, that means there are no overlap. Something occur in A cannot be occur in B. The probability for A or B will be equals can be written as probability for A unit or B, right, equals the probability of A then plus probability of B. We already know this before. That is the additional rule for disjoint event. Now, how about if these two events A and B are just in general? That means they may not disjoint. Right? That is called general addition rule for any two events A and B. In this Venn diagram, this is event A, this is event B. Looks like they are not disjoint. So what is the probability for A or B in this situation? The probability in this diagram, the probability of A is this. The probability of B is this. And what we want is A or B, the probability for A or B. If we just use the previous formula, probability A plus probability B, that means we have this one plus the white part, then plus this part plus the white part. So you can see we plus the white part twice. And the white part actually is just the A and B. If we still want to use PA plus PB, then we need to minus this white part once, because we need this white part only once. So in general, the addition rule will be probability for A or B equals the probability for A plus the probability of B, then minus the probability of A and B at the same time. Then we said this one is more general. This is a special case. In this one, if A and B are disjoint, that means this probability for A and B will be equal to 0. Then this formula will go back to this formula. This is more general. This is a special case. We discuss here, we have an example to show how to use this general addition rule. The question is, what is the probability of randomly drawing either an ace or a heart from a deck of 52 playing cards? We have some facts. There are 4 aces in the pack and 13 hearts. We know that. We have 4 aces and we have 13 hearts total. However, one card is both the ace and heart. That is the ace heart. And what we want, so here, based on this fact, we have several calculations. The probability for a card, for a random card, to be an ace is, because it's a random, equally likely random event. So we have totally 52 cards, and we have only 4 aces, so that the card for a random card to be an ace will be equals 4 over 52. So that is how we assign this probability. Same thing applies to the probability for heart. We have 13 heart, we have 52 total card. So this P heart equals 13 over 52. And the probability for ace and heart, because we have only one. One card is both an ace and heart. So that's also 1 over 52. Now what we want is, what is the probability for a card to be an ace or a heart? If we want to use the formula in the last slide, for easier, so this is event A, this is event B. This is A and B, and this is A or B. So we know the probability PA or B equals PA plus BB minus PA and B. Right? The reason is we use this formula is because event A is ace and event B is heart are not disjoint. That means a card can be an ace and a heart at the same time. They are not disjoint. So we need to use this formula. We cannot use only this part. This part only applied to disjoint event. And these two events are not disjoint. So PA plus PB minus PA and B. So PA equals this, PB equals this, and PA and B equals this one. So the 52, 52, 52 here. 4 plus 13 equals 17, minus 1 equals 16. 16, we cancel 13, we cancel 4, so that is 4 over 13. Next one, we are going to discuss the conditional probability. We already know the conditional distribution. It's a very interesting topic we discussed before. Now we are going to discuss the conditional probability. Actually, conditional probability is more frequent than you may think. For example, if the outside is cloudy, I ask, is it going to rain or not? Okay, so now your answer depends on where you are. So here it says if you are in Los Angeles or if you are in Seattle, your answer may be, the probability may be different. Or another example is if you are in a tropical region or you are in the desert, definitely your answer will be different too. The second example is what is the probability that you win the jackpot? Again, your answer will depend on some information. For example, I just ask you, what is the probability that you win the jackpot? You say, okay, that probability is too small. It's very, very, very small. If I tell you, the winner is in our class, in our classroom, so now your answer may change. Now you know you're going to have much larger probability that you win the jackpot because the winner is already inside our classroom. That is the information I give you. So when you answer these probabilities, usually you are going to consider some condition. So that is called the conditional probability. Conditional probabilities reflect how the probabilities of an event can change if we know that some other event has occurred or is occurring. Our brains effortlessly calculate the conditional probability, updating our degree of belief with each new piece of evidence. For example, another one asks you, what is the probability for you to pass my class? You may have some answer. Now, if I tell you additional information, I'm famous for give all students A, then you may change your answer, right? Or if I tell you I'm famous for fail every student, then your answer definitely will be changed also. So that is also the situation of conditional probability. So how to calculate the conditional probability? We have a formula here. The conditional probability for event B given event A is, definitely we need to assume probability for event A is not equal to 0, otherwise this formula cannot be applied. So the probability for event B given the condition of event A, we write in this format, probability of B, so of B given the condition of A will be equal to probability of A and B divided by probability of A. So this one you can imagine this is divided by A. So that's why A is here. Although it is not, I just use this method, easy to memorize. So B, the probability of B given the condition of A will be equal to A and B divided by probability of A. Now let's consider another formula. what is the probability of A given the condition for B? Are these two equal? Alright, now we use the same idea here. Probability of A given the condition B will be equal to probability of A and B. Said A and B. A and B, B and A is the same thing. So A and B here, then divided by the probability of B here. So you can see probability of B on the condition of A will be equal to this over PA. Probability of A on the condition of B is the same thing divided by PB. So definitely these two are different. So PBA is not equal to PAB. So they are different. Again, we have an example to see how to do this. I copy this formula to here, so easier for you to see this. We assume a number set includes whole numbers from 1 to 100. So 1, 2, 3, 4, 5, all the way to 100. We define event A as the number is an even number. So event A is an even number. We define event B as a number is in the fourth quartile. That means it is 76, 77, 78, and all the way up to 100. The first quartile is from 1 to 25. The second is from 26 to 50. The next one is from 51 to 75. And the fourth quartile, which is B, is from 76. So we write here, okay, 76, 77, 78, all the way to 100. And this one is even number, means 2, 4, 6, and all the way to 98 and 100. So this is event A. This one is event B. Now we calculate some. We know some fact and we do some calculations for conditional probability. What is the probability of A? Probability of A here, we know the whole set is from 1 to 100. So there are totally 100 numbers. And A means 1, 2, 4, 6. So definitely this is equally likely phenomenon, equally likely event. So the A will be equal to the probability of this plus the probability of this plus of this. So actually we have 50. So PA equals 50 over the total, which equals 100. That PA equals 50%. PB, the same thing. The total number is 100 and B is 76, 77, 78. So we have totally 25 numbers because this is in the fourth quartile. So 25 over 100, so equals 25%. The next probability is B and A. Means event A and event B at the same time. So must be an even number and in the fourth quartile. If we compare these two sets, so 2 is not here, 4 not here, 6 not here, okay, only 76 is here, 77 is here but not here. So we find that the overlap means we have only 13 numbers, 76, 78, 80, and all the way to 100. So that is the probability is 13 over 100. I don't think we have any problems to understand these three. Now, the new, maybe a little bit difficult to understand is this part. This is a conditional probability, and this is another conditional probability. This is the probability of B on the condition of A. This is the probability of A on the condition of B. So let's see what's the one. This one means the condition is A. That means the number is already an even number. And what is the probability that it is a B, that means it is in the fourth quartile. Okay? Let me repeat. The number is already in A, means it's already an even number. And what is the condition for it to be in the fourth quartile? So if it's already in A, then that means we have only 50 possibilities. 2, 4, 6, and all the way to 100. We have only this 50. Now, the probability, the event B means it is in the fourth quartile. We know 76, 78, so we have 13 possibilities. So the probability of B on the condition for A will be equal to 13 over 50. So this is 50, and this one is give us both 13. Both A and B give us 13 possibilities. Okay? Now the next one is what is the probability of A on the condition for B? So the condition is B. That means first one, the number must be a B, from B. So B means it's in the fourth quartile. So we have only 25 possibilities, 76, 77, 78, all the way to 100. So we have only 25 numbers. We have only 25 possibilities. If the number is already satisfied this B, then it can only be this 25 possibilities. Now, what is the probability that it is a A? That means it is an even number. So here, 76, 78, 80, 82, and all the way to 100. Again, that has only 13 possibilities. So this probability will be equal to 13 over 25. We mentioned in the last slide, PBA may not be equal to PAB. So here, PBA equals 13 over 50, PAB equals 13 over 25. They are not equal. Okay, up to this point, we only calculated the probabilities from the fact. We know that. We haven't used the formulas we discussed in the last slide. Now we are going to use the formulas, the conditional probability to calculate these two, to verify this one is correct. This one is correct. This one is correct. We know this is good. This is good. We just want to verify if we use the formulas, can we get the same result? Okay, we know this because the formulas need to use PA, PB, and PA and B. So PB on the condition of A equals PA and B on the top, PA here, again, this is the trick, okay? PA on the bottom. So PA and B is here, PA and B, PB and A is the same, right? Alright, so that equals 13 over 100 here, and this one, PA equals here, 0.5, okay, that one equals 13 over 50. Oh, that equal to this one. So this one is good. Then PAB equals PA and B on the top, B and A the same, right? And PB on the bottom. Again, keep in mind, this is the trick. So you cannot think this is divide, but you use this method to memorize the formula. So on the top equals A and B equals same thing, 13 over 100. On the bottom, PB is here, okay, 0.25. So this one equals this. Alright, now this one yes, that one is also equals this. So this one is good too. So we verified the formula. Right? In this example, we can easily find this too, but sometimes it's not easy. Then how we calculate the conditional probability? We always use the formulas. Conditional probabilities are very, very important, but they also, unfortunately, is sometimes very difficult to understand. So we we discuss a very interesting paradox. to show that how to understand the conditional probability. That is called Bertrand box paradox. There are three boxes. Three boxes. So this is box 1, this is box 2, and this is box 3 here. Each with one draw on each of the two sides. So we have one draw on this side, another draw on that side, the opposite side. Okay, we have two draws, one is here, another one is opposite, and we have another draw here and another draw there. So we have three boxes. Each box has two draws on both sides, on each side. And in each draw, we are going to put a coin. One is gold coin or silver coin. So for this one, we may put a gold coin on the front and a gold coin on the bottom, on the outside. And this one, we will put a gold in the front and earth on the other side. And this one, silver and silver. Definitely random, but we are going to do like this. Now, the interesting thing is, first one, I'll let you randomly choose one box. You cannot see the corners, but I'll let you randomly choose one box. Suppose you choose this one, or you choose this one, you choose this one. Each one you have 1/3 of a possibility, probability. Suppose you choose this one. Now, once you choose the box, you choose a random draw. For example, you said, okay, I open the drawer on the front. Or I said, I'll open the drawer here, in the front or in the bottom. Anyway, you have two possibilities, front and back. Once you randomly choose one box, and you randomly choose one drawer, you open it, and you find a gold coin. That is all the information we know. You randomly choose one box. Once you obtain the box, you randomly choose one side. You open it, you find it is a gold coin. The question is, what is the chance of the coin on the other side being gold? Can be gold, can be silver. And what's the probability that the other side is also a gold? So how to calculate this? Alright, now let me draw this again as GG, GS, and SS. Okay, first line we think, because you randomly choose one, then one box, this or that, then you randomly open a drawer, and it is gold. So that means definitely it cannot be this one, because this one has both silvers inside. So it's not this one, because that is the condition, right? The condition is you open one, okay, you find it is gold. So this one does not satisfy the condition, so it's not this one. Now look at this. You choose this one, both 50% possibility. Not 1/3 anymore, because this one is not possible. So 50%. Now you open one, you find the gold, okay? So this one is gold, this one is gold. Yeah. Okay, the other side, what's the probability for it is to be gold? So, okay, this one here, gold, this one is gold. So you can, that means once the first gold can be this and can be this. So the other side, opposite, can be gold or can be silver. So each one has 50%. So the probability for the other side to be gold is also 50%. So that is one way to solve this problem. Now, let's think another way. We still have the same box, right? Same box here, and we know that S cannot be here. We don't care about this one. So that's GS. Okay, that is. So that is GG, and this one is GS. And this one is gone, so we just ignore this because this is impossible. Now, we have 4 we have 2 boxes, but we have 4 drawers, right? And when you open these drawers, it's totally random. That means each one you have same probability to open this, to open this, to open this, to open this. Now, you know when you open the drawer, it is a gold. So that means it cannot be this one. It can only be this, can only be this, can only be this. When you first choose the drawer to open, it can only be this because you already found a goal. So it can only be this, can only be this, can only be this, cannot be this silver. So once you find the gold here, right, the opposite side is gold. If you open this one, the opposite side is gold. If you open this one, the opposite side is silver. So now we know you have an equal probability to open this, and open this, because you cannot open this one. This one is silver. So you have 1/3 of here, 1/3 of here, 1/3 of here. Then, if you open this, you find gold outside. If you open this one, you find gold outside. You open this, you find the silver on the other side. So that means the other side is the gold, has a probability of 2/3. So we have 2 ways to explain this. And which one is correct? This one we said, okay, half. Because you choose this box, this box. And here you choose this drawer, and this drawer. I'll let you think about this. We can discuss later time.